Okay, what you see here are some examples of oscillating objects that we see in daily life. Okay, first, these are bobbleheads. You just compress them and release, or you pull them up and release. You will see them oscillating up and down. Okay, they can oscillate sideways also. Next is a spring block system suspended vertically. This one also, you pull the block down a little bit and release, you will see it oscillating up and down. Fine. The third example is a swing, okay, in which a person moves back and forth in an angular manner like this, not along a straight line. Okay. So this will be along a circle, I can say. Not a it doesn't complete a circle, but the motion will be along a circle. And the last example you see is that of a pendulum, which swings back and forth. This also swings along a curved path. Fine. So you imagine these systems moving. Basically, oscillation is nothing but to and fro motion. Okay. So we are going to discuss the mechanics of such systems. What are the forces which are involved? How to describe mathematically describe the motion of such objects? How to predict the position of an oscillating object in future at a certain time? Okay. How much time it will take to complete the oscillation and such things. Fine. Uh, can any of you give me any other examples of oscillating systems that you can imagine? You can like just look around you. There will be many examples. For example, let's say there is wind blowing and you look at the curtain. Okay, the curtain will mostly be oscillating back and forth. Okay, uh, there are many examples that you can think of and that you can observe in daily life also. So systems which undergo to and fro motion are called oscillating systems. Fine. And basically, to and fro motion is called oscillation. Next, there is something called periodic motion. As the name suggests, if the motion of an object or a system repeats after a certain period, okay, it's called periodic motion. Now, I want all three of you to think of some examples where the motion of a system repeats after regular intervals of time. Make it fast. Some daily life examples. Any examples of periodic motion that you can think of? I got one answer as tides, like, okay, waves in the sea. Okay, high tide, low tide. Fine. Usually on full moon days, we have high tide in the sea. That is due to the gravitational pull of the moon. Okay, makes sense. Others, any examples of periodic motion that you can think of? I got another answer as revolution of Earth around the sun. Good. Earth takes a fixed amount of time to complete a revolution around the sun, and it repeats itself. Okay. And okay, so one example we got is high tide, low tide. Another example we got is revolution of the Earth around the sun. Rotation of Earth about its own axis is also periodic motion. Fine. Many examples. There are many examples that you can think of. The motion of the hands of a clock, that is also periodic. For example, you take the seconds clock. The seconds clock takes exactly 1 minute to complete one revolution, and it repeats itself. Okay, as long as the clock runs, right? That is also periodic motion. So in periodic motion, there is always a certain regular interval after which the motion repeats itself. That regular interval after which the motion repeats itself is called the time period of that periodic motion. For example, for the revolution of Earth around the Sun, time period is 365 days. For the rotation of Earth about its own axis, the time period is 24 hours, and so on. Okay. For the motion of a second's hand in a clock, the time period is 60 seconds. After every 60 seconds, that is 1 minute, it repeats itself. Okay. Similarly, for the minutes and hours hand also, you can write, you can assign a time period. Okay. So there are many examples that we can think of oscillatory motion as well as periodic motion. Okay. Now, in your syllabus, there is one particular kind of motion that we are going to one particular kind of oscillatory motion that we are going to discuss, okay, which is called simple harmonic motion. In short, we call it SHM. It's an example of periodic as well as oscillatory motion, and there are some extra conditions also which we are going to discuss. Fine. Now you observe, look at these oscillating, look at these examples of oscillating systems that we have considered. There are some systems which oscillate on a straight line, okay, which move back and forth on a straight line. Those are called linear oscillations. Fine. And there are some systems which oscillate along curved paths, like they swing back and forth. Fine. Such oscillations are called angular oscillations. So in this chapter, we'll be learning how to describe the motion of linear oscillations as well as angular oscillations mathematically, how to find out their time period, and how to describe other characteristics also. Okay. So let's start with linear oscillations. You'll understand what is simple harmonic motion. It is one particular case of periodic oscillations. Okay. What is the condition? We'll discuss in some time we'll discuss. You consider linear oscillations first. As the name suggests, there is an object, or you can imagine an object oscillating along a straight line. Suppose there is some object oscillating on this line, moving back and forth. Now, for every oscillating system, for every system that moves back and forth, you can assign two extreme positions. Okay. Let's call this end of the straight line as A and the other end as B. As the object oscillates on this straight line back and forth, these are the extreme positions that it reaches. Okay. So you can call them as left extreme and right extreme, or you can call them as negative extreme and positive extreme. Okay, these are some common terms that we are going to use while describing oscillatory motion. Fine. So as an object oscillates back and forth on a straight line, the extreme positions can be called negative and positive. Okay. Now, as it oscillates back and forth, first, or let's say, in some part of the oscillation, it moves from A to B, and in some part of the oscillation, it moves back from B to A. Oscillation is the to and fro motion, no back and forth motion. Okay. Now you all imagine an object oscillating between A and B, okay, moving back and forth between A and B. Tell me, what is the velocity of such an object when it is at A and when it is at B? Think carefully, visualize carefully, okay? Imagine an object moving back and forth between A and B. What velocity will it have when it is at A or when it is at B? Okay, Yusuf, unmute and tell me what exactly happens when the object reaches A and what exactly happens when the object reaches B as it is oscillating between A and B.
It stops and change direction.
Correct. Correct. Okay. As when it goes from A to B, it's moving in the rightward direction. At B, it reverses its direction. So it has to stop for a moment. Same at A also. It is moving towards left. And at A, it reverses direction. okay, and starts moving to the right. So it has to stop for a moment. If it is stopping for a moment, then what is the velocity at these positions?
So 0.
Zero, correct? Okay, so all three of you have understood that at extreme positions, the oscillating object will be at rest. So velocity at A or velocity at the negative extreme is zero, and velocity at the positive extreme is also zero. Fine. At the extreme positions, the velocity is zero, but the oscillating object does not stop there, does not stay there. Okay, velocity is zero only for a moment, only for an instant. Okay. So suppose the object is at A. When it is exactly at A, it's at rest, but you know it starts moving forward. Now, based on this, you all tell me, okay, exactly at the position A, the object is at rest, but then it starts moving to the right. So something is starting to move from rest. So it must be accelerating. From zero, the next moment, it will be moving. The velocity becomes non-zero, means it has acceleration. So I want you all to think carefully and tell me, as the object starts moving from A, okay, consider A itself. As it starts moving from A, what is the direction of its acceleration? Let's visualize what happens. The object is at rest at position A and it starts moving. So it gains velocity. Fine. And as it reaches B, it has to stop again because it should take a turn. So when it reaches B, or as it reaches B, it will have to slow down. So this is what happens as the oscillating object moves from A to B. Similarly, when it is moving back from B to A, when it starts from B towards A, it will be slow, but it will gain velocity. Its speed will increase. And as it approaches A, it will have to stop there and reverse direction. No, so the speed will have to decrease again. Fine. See, you can imagine cases where the object moves with constant speed, suddenly collides with something and reverses its direction also. But in a real life situation, that is not possible. Fine. Like hypothetically, an object can go with constant speed from A to B, undergo elastic collision, and come back with the same constant speed from B to A. Such things are possible in imagination, but in real life, it's not. Okay. So when the object starts moving from A, which is the extreme position where velocity is zero, it gains velocity to the right, means its acceleration is in this direction to the right. That is how it is gaining velocity in that direction. Okay. But look at what happens as it approaches B. Okay, it's in forward motion itself. Okay, consider the green arrows only. As the object approaches B, its direction of motion is to the right, but its speed is decreasing. We had discussed this back in kinematics itself. When or what decreases the speed of an object? Tangential acceleration, which is opposite to its velocity, is what decreases the speed of the object. Okay, so as it approaches B, the object is slowing down. Slowing down means acceleration should be opposite to velocity. So it will be like this. Okay. Next, you imagine it starting from B towards A. If it is starting from B towards A, that means it is accelerating towards A. So acceleration will be to the left. And as it approaches A, it has to slow down. Slowing down means acceleration should be opposite to its velocity. When it is approaching A, it's moving to the left, but it's slowing down, means acceleration must be to the right. Okay, what we are observing or what we are noting down here are some basic characteristics of oscillating systems. Okay, for now we have restricted our discussion to linear oscillations, oscillations on a straight line. So at extreme positions, the velocities are zeros. Close to negative extreme, acceleration will be to the right in the positive direction, and close to positive extreme, acceleration will be to the left, that is in the negative direction. Okay. So it stops at extreme positions, then gains velocity, again stops at the other extreme. Therefore, the velocity of an oscillating object is variable. Not just as a vector, even the magnitude of velocity, which is basically speed, is a variable. Oscillating objects do not move with constant speeds. Okay. Yes, hypothetically, you can imagine it to be moving with constant speed from A to B, colliding and coming back. But that does not happen in simple harmonic motion, or in real life oscillations. That does not happen. Okay. Next, you think of acceleration. Acceleration also clearly is a variable, because when the object is at A, acceleration is to the right. When the object is at the positive extreme B, acceleration is to the left. It's in the negative direction. So definitely acceleration is changing. Fine. Now let's go back to these examples that we have considered. In all these systems, there will be one position of the oscillating object. Okay, one position of the oscillating object from which, if you release the object also, it will not start oscillating. Okay, for example, you take the swing itself. Okay, if the swing is exactly vertical and you leave it in that position, okay, swing or simple pendulum also, if it is in this position, in the vertical position, if you leave it there, it won't start oscillating. What does that mean? Okay, even spring block system and these bobble heads that are given also, at one particular position, if you gently release them, there will be one position from which they won't start oscillating. From anywhere above that you release, it will oscillate. From anywhere below that you release, it will oscillate. But one position will be there from which, if the system is released, it won't start oscillating. Okay. Now we are releasing a system from rest, means velocity is zero, and we see that at one position it doesn't start moving, means it doesn't gain velocity, means acceleration is also zero. Okay. So for every oscillating system, there will be one position. It could be exactly between the extremes or somewhere between the extremes. Okay. For simplicity, we'll assume one position exactly between the extremes. There will be one position where acceleration is zero. And it's obvious. See, uh, in real life, velocities, accelerations, they don't change abruptly. They change gradually only. Okay. Now, close to A, close to the negative extreme, acceleration is positive. Close to the positive extreme, acceleration is negative, then definitely there will be some position in between them where the acceleration is zero. From positive, if it has to change to negative, somewhere it will have to touch zero. Okay, so there will be one position where the acceleration is zero. And if you leave the or release the oscillating system from that position, it won't start moving. That position is what we call as mean position. Okay. It may be exactly between the extremes. In some cases, it may not be exactly between them also. You'll understand as we solve problems. But what is mean position? Mean position is the position at which acceleration of the oscillating object is zero. And when will acceleration be zero? When net force is zero. Newton's second law. That is what we call as mean position in oscillating systems. Okay. If you release the system from mean position, it won't start moving. Release it from the left side of mean position, it starts moving to the right and it will swing back and forth. Release it from the right side of mean position, it starts moving to the left and it will swing back and forth or oscillate back and forth. But when released exactly from mean position, it does not start moving at all. Okay. So understand these terms: extreme positions, mean position, what will happen to velocity of an oscillating system, what will happen to the acceleration of an oscillating system. Okay. Now velocity is changing, so there is acceleration. And if there is acceleration, there must be forces involved. Whatever is the direction of acceleration, same is the direction of net force acting on the object. From Newton's second law, we know F net equal to ma. Okay. Now you see, anywhere on the right side of mean position, acceleration is to the left. What does that mean? You release the object anywhere on the right side of that dotted line. Okay. For example, you release it here, it starts moving this way. You release it here, it starts moving this way. Acceleration is to the left. Anywhere on the left side of the mean position, you release the object here, it starts moving this way. You release the object here, it will start moving this way. Acceleration is to the right. Okay. You can clearly like imagine, or you can easily visualize this if you think of a simple pendulum. Simple pendulum in the vertical position, if you release, it stays like that only. But if you pull it to the right and release, it will start swinging to the left. If you pull it to the left and release, it will start swinging to the right. Okay. So what it shows is anywhere to the right side of mean position, the net force is to the left. And anywhere on the left side of mean position, the net force is to the right. And this is very, very important, the direction of force. So F net, anywhere on the right side of anywhere on the right side of mean position, the net force is to the left. And anywhere on the left side of mean position, the net force is to the right. So you look at the direction of net force. Can any of you describe the direction in which net force acts? Of course, there's no fixed direction, it keeps changing. But is there something common, or is there something that it is trying to do? Okay, what Vanilla said is correct. Net force on an oscillating system is always directed towards the mean position. Okay, we can just by observing oscillating systems, we can arrive at this conclusion. F net is always directed towards the mean position. That means the net force acting on an oscillating object is always trying to bring it to the mean position. If it is going away from it, it will slow it down. If it is coming towards it, it will speed it up. Okay, so it wants the object to stay at the mean position. It will try its best to do that. Fine. So these are the basic characteristics that you need to understand about an oscillating system. We are, as I said, we are restricting our discussion to linear oscillations for now. In angular oscillations, whatever force does will be done by torque. Okay, whatever force does in linear oscillations will be done by torque in angular oscillation. So it's not very difficult to deal with. We will do that later. So oscillation involves variable velocity, variable acceleration, variable force. And an oscillating system has something called extreme positions and a mean position. At mean position, the net force on the oscillating system is zero. If you release it from there, it won't start oscillating. If you release it from anywhere other than the mean position, it will try to come to mean position. But by the time it comes to mean position, it may have some velocity, inertia of motion. So it will cross the mean position and go to the other side. Then it will again come back to mean position, but then it will have some velocity. So it will cross the position and go to this side and so on. That is how it effectively oscillates. Okay. Now, the force, since it is always directed towards mean position, basically what the net force is trying to do is, it is trying to keep the object at the mean position. It may succeed in that or not, that's a different story, but it is trying to keep it at mean position. So we call it as a restoring force. The force is trying to restore that position. It wants to bring the object back to that position and keep it there. Okay, so we call it as a restoring force. Every oscillating system will have restoring force or multiple restoring forces acting on it. Without that, oscillation is not possible. There should be some force trying to bring the object back to mean position. Only then oscillation is possible. Okay, let's talk about this in some systems. For example, consider a spring block system like this, a horizontal spring block system. Assume the surface is perfectly smooth. Okay, let's say there is a block connected to a spring. Quite easy to imagine. At one particular position where the spring is in natural length, if you release the block, it won't start oscillating. Okay, let's say this is the natural length of the spring. At natural length, the spring does not exert any force. The other forces acting on the block are its weight and normal force, which will be balanced, so it won't start oscillating. But you pull it to the side and then release. Okay, or you displace it from natural length and release. Okay, so if you release it from this position, basically you are releasing it by stretching the spring. Then what will happen? There will be a net force acting to the left. If you take it to the left of that mean position and you release it, there will be a net force acting to the right. Okay. So in this case, what is the restoring force? Which force is trying to restore the position of the object? Think about it carefully and answer. What is the name of the restoring force in this spring block system? Is the block coming back to its or trying to come back to that position because of gravity or because of normal force or because of spring force or multiple forces? Think carefully and tell. Which force is the restoring force? It's a simple question. Eh? What force brings the block back to its mean position in that spring block system? Vanilla, what do you think? There are three forces acting on the block. Its weight, normal force from the table, and spring force. Which force do you think is the restoring force in that case?
So the spring force.
Correct. Okay. So restoring force is nothing but the net force acting towards the mean position. Now, weight and normal force act vertically. Spring force acts in this direction or in this direction, depending on the position of the block. So restoring force is the spring force in this case. Okay. Next, you consider a pendulum oscillating back and forth. Can any of you tell me if we like, okay, I hope it is clear, like from everyday experience, you should be knowing that if you release the pendulum from this position, the position one, it won't start oscillating. So obviously that is the mean position for the pendulum. You take it to the right of mean position and release, it will start moving to the left. And you take it to the left of mean position and release, it will start moving to the right. Same with a swing also. Same happens with a swing also. So in this case, what is the restoring force? What force brings or tries to bring the pendulum back to its mean position? Yusuf, what do you think?
So is it gravitation?
Good. It is gravity. Okay. See, gravity actually acts in the vertically downward direction, but it will have a component along this path. That component of gravity is what behaves as the restoring force. So in this case, gravity component. Fine. So for every oscillating system, there will be one or more forces which will be directed towards the mean position and they will contribute to the restoring force. There could be multiple forces also. Right. Now you can see that when the object is on the right side of mean position, the restoring force is to the left. And when the object is on the left side of mean position, the restoring force is to the right. Okay. So what we are going to do is we are going to assign the mean position as 0. This is not a rule. The object could be oscillating anywhere on the x-axis, but let's assume for now, let us consider the mean position to be x equal to 0. So right side becomes positive x-axis, left side of the mean position becomes negative x-axis. So when the position of the object is positive, force is negative. When position of the object is negative, force is positive. Fine. Or to be more generally correct, you can say like this. See, that x is equal to 0 is the mean position, no? When object is on the positive side of the mean position, means the displacement is positive. Displacement from mean position is positive, force is negative. When object is on the negative side of the mean position, means displacement from mean position is negative, force is positive. This will be true in all cases. Okay. Let me repeat what I just said. Let's copy this diagram. This is also a general characteristic of simple harmonic motion. irrespective of what position exactly is the mean position. So it doesn't matter. It doesn't have to be x is equal to 0. Let it be any value. Okay. When object is here on the right side of mean position, its displacement from mean position is positive. Okay. What I'm saying is, let's say the mean position is x is equal to 5 centimeters. Then this coordinate will be some x is equal to 7 centimeters randomly. Then displacement from the mean position, if you see, it is 2 centimeters, positive 2 centimeters. Okay. So if displacement from mean position is positive, then the force acting there will be negative, or the restoring force is negative. Okay, F stands for restoring force. And you can also consider something like this. If displacement from mean position is negative, means the object is on the left side of mean position, then the restoring force will be positive. So basically, in simple harmonic motion or in an in a naturally oscillating system, what happens is the restoring force will have a direction opposite to the direction of displacement from mean position. Okay. Usually, we use the symbol S for displacement, but here we are going to use the symbol X itself for displacement. If it is oscillating horizontally, we use X. If it is oscillating vertically, we use Y. But remember that X or Y in this case stand for displacement from mean position. So you can say that the restoring force is always opposite to displacement from mean position. So they will have opposite signs. If displacement from mean position is positive, the restoring force will be negative, and reverse. If displacement is negative, restoring force will be positive. Okay. Now consider the spring block system itself. You know that the force exerted by a spring will be greater when the spring is stretched further. Okay, it depends on how much the spring is stretched or compressed. So if you pull the block to the side only a little bit, if you pull the block away from the mean position only a little bit, there will be a small amount of force acting on it. If you pull it further away, there will be a greater amount of force acting on it. Fine. Same thing happens with simple pendulum also. You consider the angle by which it is taken away from mean position. Let it be theta. If that angle is theta, then the component of mg, which will be trying to restore its position. See, mg is actually in the vertical direction. No? The component of mg which tries to restore its position will be mg sine theta. Now, as theta increases, sine theta increases. Okay. When it is close to the mean position, there will be a small component of mg trying to restore it. But when you take it further away from the mean position, somewhat like this, okay, you imagine the circle along which it moves, or the curved path along which it moves. Now you will see that there is a much larger component of mg trying to restore its position. So usually what happens in oscillating systems, the restoring force that is there will not be constant. It will not be uniform. It won't be the same everywhere. The further the system goes away from mean position, stronger the restoring force will be. I'm not saying this is compulsory, but in most cases it will be like this. Restoring forces are non-uniform. Okay, how much restoring force is acting on an oscillating object depends on how much the oscillating object is away from the mean position. So the direction of restoring force is always opposite to the displacement from mean position, and the magnitude of restoring force also depends on the magnitude of displacement from mean position. Fine. How exactly it depends? It depends on the situation. It varies from case to case. Now, we are talking about one particular case of periodic oscillatory motion called simple harmonic motion, right? SHM. The condition for simple harmonic motion Or when do you call oscillatory motion a simple harmonic motion? The condition is that the magnitude of restoring force should be proportional to displacement from mean position, directly proportional. Then we call it simple harmonic motion. Okay, so it is clear that restoring force is always directed towards mean position. So if displacement is positive, force is negative. If displacement is negative, force is positive. So the direction of restoring force is always opposite to displacement from mean position. That is true for any kind of oscillatory motion, not just simple harmonic motion. And it is also understood that the strength or the magnitude of restoring force can vary based on how much the object is displaced from mean position. If it varies in such a way that the magnitude of restoring force is proportional to displacement from mean position, then it is called simple harmonic motion. So this is the condition for SHM. Very, very important. In fact, the most frequently used equation in this chapter is this only, force proportional to displacement. Okay, and you know its direction is opposite to displacement. So if you write it in vector form, it becomes like this: F is equal to, or F proportional to, minus X. Actually, we should write F proportional to minus S, where S stands from displacement from mean position. But usually in all books, even in question papers, it is taken as X. But you need to remember, X does not represent the position of the object. It represents the displacement from mean position. Okay, you can write it as S also, nothing wrong in that. And the proportionality constant, you can assign some value. So the restoring force will be of the form minus K X, or you can also write F is equal to minus K S. This is the relation between force and displacement in simple harmonic motion. F stands for net force, restoring force. Okay, so basically it's the net force towards mean position, will be equal to minus K times S, where S is the displacement from mean position. And the constant that we keep in between is simply called the force constant. So any system which obeys a relation like this, any system on which this kind of a force acts, will be executing simple harmonic motion. So this is the condition for SHM. Fine. So we have F net, the net restoring force, is equal to minus K X. Okay, for simplicity, I'm using the symbol X itself. And we know F net equal to ma. So let us equate this to ma. Therefore, you get acceleration is equal to minus K by m times X. You can call this also as the condition for SHM. If an object accelerates in this manner, where acceleration is proportional to displacement from mean position and direction is exactly opposite, it will be executing simple harmonic motion. So simple harmonic motion is one particular case of periodic oscillatory motion where the force is proportional to displacement from mean position, or acceleration is proportional to displacement from mean position. Okay. If it is not proportional, then it can be harmonic motion, but it won't be simple harmonic motion. It can be oscillation, but you won't call it simple harmonic oscillation. Okay. For it to be simple harmonic, this is how they should be related: force proportional to displacement and acceleration proportional to displacement. Okay. Now, we'll be doing a little bit of mathematics here. We know how acceleration is related to displacement. So based on where the object is, you can tell how much acceleration it has. But that's not the only thing we are interested in. We should prove that this is periodic. Okay, we should find out what is its time period, what is the period after which it repeats the motion. We should be able to tell where it will be after some time, with what speed it will be moving after some time. So we'll have to derive some equations here. The equations we are interested in are, first, the position time equation, position velocity equation, velocity time equation, okay, acceleration time equation, all these things. You should be very comfortable deriving all these. Okay, so let us start working on this. You have A in terms of X. The K by M that you see in between A and X is a constant. K is the proportionality constant between force and displacement. M is the mass of the object. So K by M becomes a constant. Okay. Now, can you think of, see, this is variable acceleration, obviously. So you cannot apply equations of kinematics. Okay. In oscillations, you cannot apply equations of kinematics. Absolutely useless because acceleration is variable. It keeps changing from position to position. So how do we write equations for the object? We'll have to rely on the definitions. The basic equations we have are acceleration is equal to dv by dt, rate of change of velocity with respect to time. Velocity is dx by dt, rate of change of displacement or position with respect to time. And we have A is equal to v dv by dx as well. This is a scalar equation. I hope you all remember that we had discussed these in kinematics. So these are the basic equations from definitions of these quantities. Now we have A in terms of x. The only equation which relates A and x is this third one. A is equal to v dv by dx. So what we are going to do is we'll write minus k by m multiplied with x is equal to acceleration, that is nothing but v dv by dx. Nothing wrong in doing this. Okay, what we are trying to do slowly here is relate velocity to displacement. V stands for velocity, x stands for displacement from mean position. We are trying to relate them so that we can predict what will be the velocity of an object based on the position during its oscillation. Okay. Now in this derivation, we are going to call this k by m as omega square. You'll understand why it is called as omega square. Okay. So you can write v dv by dx is equal to minus omega square times x. Send the x term to that side. You get v dv is equal to minus omega square x dx. Now you can integrate both sides. Okay. Omega square is a constant. Omega square is k by m. K is the force constant, m is the mass of the system. Those are constants, so we can put it outside the integral. You will be left with this. Now you have to substitute some limits. Integral you can do, but you will have to substitute limits also. All of you recollect and tell me, do you know any position or is there any position where you know the velocity of the oscillating system? Good. We know the velocity of the oscillating system, or we know that the velocity of the oscillating system is zero at the extreme positions. So we are going to use that as one of the limits. Just a moment, let me adjust this. Right, whether it's the positive extreme or the negative extreme, we know that the velocity there is zero. Now see, as the object oscillates back and forth, there is one position where the net force on it is zero. We call that as mean position, right? One side of the mean position, we are calling it as positive. The other side, we are calling it as negative. Assume the object moves to a maximum distance of capital A on one side of the mean position. Okay. So displacement at the positive extreme will be x is equal to plus A. And assume it moves the same distance to the negative side as well. This is not compulsory. Okay. But let's consider a simple example like this. Let's visualize a system which moves to the same distance on either side of the mean position as it moves back and forth. So this distance is also A, but if you write it as displacement, then this will be minus A. Okay. So when the displacement from mean position is minus A or plus A, the velocity becomes zero. This magnitude A is what we call as amplitude of oscillation. Okay, we are considering a case where the object moves to the same distance on either side of the mean position. As I said, it's not compulsory, but let's begin with a simple case like this. That maximum distance to which it goes away from the mean position is called the amplitude of oscillation. So from mean position to positive extreme, the distance is amplitude. From mean position to negative extreme also, the distance is called amplitude. So total distance between the extremes becomes 2 times the amplitude. Okay, let us denote amplitude by the symbol capital A. So the displacement at negative extreme will be minus capital A. Displacement at positive extreme will be plus capital A. Those are the displacements where we know the velocity for sure. Anywhere else, we don't know its velocity. So one of the limits for integration is going to be taken that. So let's assume initial velocity is 0. Position, it is your choice. You can assign minus A as initial position or plus A as initial position, doesn't matter. Let's take it as plus A. Okay. Next, final velocity. Final velocity, let's take it as V when it is at some random position X. Okay. Can one of you quickly tell me what is integral V dV? Or on the right hand side, what is integral X dx? Basic formula for
X
integration.
by 2, sir.
X square by 2. Okay. On the left hand side, integral V dV becomes V square by 2. So you can write V square by 2 and you still have to substitute limits. Let's say 0 to some velocity V is equal to minus omega square times X square by 2, and there also you'll have to substitute limits A to some random coordinate X. Okay. Now you put the limits. You get V square minus 0 square divided by 2 is equal to, on the right hand side, you have omega square times X square minus A square divided by 2. And see, once you substitute the limit, it is becoming A square. So it wouldn't have mattered whether you had taken plus A here or minus A here. Okay, because when you square it, it's ultimately going to become A square itself. So it doesn't matter whether you substitute plus A or minus A. You will get this relation. The divided by 2 will get cancelled. Send the minus inside on the right hand side. Effectively, what you get is V square is equal to omega square times A square minus X square. Very useful equation to solve problems based on simple harmonic motion. So what does this equation relate? It relates speed to displacement in simple harmonic motion. Okay. But there are some things that you need to know. You need to know omega. Okay. What did we call as omega square? K by M was called as omega square. So you need to know that term, K by M, and you need to know the amplitude of oscillation. Then you can tell what is its speed at any position. You can even assign a direction. If the position is to the right of mean position, direction will be to the left. If position is to the left of mean position, direction will be to the right. So this is how speed and displacement in simple harmonic motion are related. Okay, remember X stands for displacement from mean position. Okay, so what we got here is something very useful for solving problems as well as for further derivations. We got a relation between V and X. And using the relation between V and X, you can derive or you can bring time into the equation. If you know how V and X are related, by using V is equal to dx by dt, you can bring time into the equation, which will be even more important because once you get time into the equation, you'll be able to tell the position of the oscillating object at any time, where it will be after some time, or how much time it will take to reach somewhere. Such things you will be able to find out. Okay. So follow this derivation very carefully. The final result is also very important. So we got V square as omega square times A square minus X square. So V becomes square root of the right hand side. So omega root A square minus X square. Okay. By definition, velocity is rate of change of displacement with respect to time. So you can write this as dx by dt. Now we are going to relate x and t. Means displacement from mean position. We are going to relate it to time. Keep the x terms on one side and t terms on the other side. So you get dx divided by, dx will never be written in the denominator. Okay. You won't be able to integrate if you do that. Dx, dt, dv, dy, they should always be kept in the numerator itself. Okay, so we'll send a square minus x square to the other side. So dx divided by under root a square minus x square will be omega times dt. Integrating this equation and substituting limits will give us the position as a function of time. Okay, but follow this very carefully. This is tricky and important also. Let's integrate both sides. Omega is a constant, you can put it outside the integral, but when you integrate, you are supposed to substitute limits. So we'll assume initial time is 0. And when time is 0 means when you start observing the object, you start counting time, no? So the first instant when you started observing the object, you call that time as 0. You have to assign some position to it. For convenience, let's assume the object was at negative extreme initially. When we started observing it, let's say it was at the negative extreme. We will generalize this later also. How to write equation if the initial position is somewhere else. Okay, I'll tell you how to do that. For now, let us assume when we started observing the object, it was at the negative extreme. Or you can think of it this way also. It was pulled to the negative extreme and released at t equal to 0. So at t equal to 0, the position was x is equal to minus a. And at some random time later t, let's say the position is x. Okay. Now the right hand side omega is a constant. It will simply be integral dt, which is t itself. Integral dt becomes t. You substitute limits 0 to t, it will still be t itself. So the right hand side simply becomes omega t. What about the left hand side? Can any of you tell me how to integrate dx by root of a square minus x square? We had discussed this when we discussed uh, different types of integration or different methods to do integration, and some of you may have used it later also. And I think we had used these in center of mass derivations as well. Yes, we had. So can any of you recollect the idea to integrate expressions like this? Yeah, Aishwarya, what you said is correct. Substitution method. So let's write this term aside first, separately first. Dx divided by square root of a square minus x square. We should integrate this by substitution. Means we should we should replace x with something else. So can any of you tell me what we should substitute x as? Such that this expression becomes simpler to integrate. Okay. We substitute x as a sine theta. Why? You have to see the term that is there in the integral. You have 1 by under root a square minus x square, no? So if you take a common or a square common, it becomes 1 minus 1 by a square times x. Or okay, let's not complicate this. Suppose you had under root 1 minus x square simply. If you substitute x as sine theta, then it becomes 1 minus sine square theta. 1 minus sine square is cos square, and under root square and root will cancel. Only cos will be left. Only cos theta will be left. That way it becomes simpler to integrate. Okay, you are simplifying the function by changing the variable. Okay, let x is equal to a sine theta. Then what happens? A square minus x square becomes a square minus a square sine square theta. That is a square times 1 minus sine square theta, that is cos square theta. So effectively, the term that is there inside the square root becomes a square cos square theta. That's okay. But when you are replacing x with something else, you are changing the variable effectively. You are changing the variable from x to theta, then you will have to change dx to d theta. Not directly change, you will have to express dx in terms of d theta. How do you do that? You do that by differentiating this. Okay. You have x is equal to a sine theta. If you differentiate both sides with respect to any one of the variables, or you can differentiate with respect to a third variable also, doesn't matter. But let us differentiate with respect to theta. Then what does the left hand side become? Dx by d theta. Right hand side, derivative of a sine theta. A is a constant anyway, it's the amplitude of oscillation. Derivative of sine theta is cos theta. Therefore, dx becomes a cos theta d theta. This is how you express dx in terms of d theta. So when you are changing variable, you have to change this as well. So in place of x, we are going to write a sine theta, and in place of dx, you will have to write a cos theta d theta. So see what the integral changes to. Therefore, integral dx by under root a square minus x square changes to what? In place of dx, you now have a cos theta d theta, and under root a square minus x square. See, a square minus x square is becoming a square cos square theta. So root of this becomes root of this. So it simply becomes a cos theta. And we see that these two get cancelled. So now it becomes a very simple integral d theta, which is nothing but theta, but you have to substitute limits for theta now, theta initial to theta final. Okay, so we have simplified the integral so far. On the left hand side, we had integral dx by root of a square minus x square, which after integration by substitution simply changed to theta. Now, when we began this integration, we knew the limits for x. We took the initial position as negative extreme, final position as some random position x. These are the limits for x. But when you change the variable, you have to change the limits according to the variable. Now we took x as a sine theta, no? When x is equal to minus a, we substituted x as a sine theta. The lower limit we are taking for x, or the initial limit we are taking for x, is minus a. So when x is minus a, you should find out what is theta. And theta limit should be substituted here. Okay. When x is minus a, to make it more easily understandable, you can say x initial is equal to a sine theta initial, and x final is a sine theta final, where theta is some new variable. Now we took initial value of x as minus a. So minus a is equal to a sine initial theta. A gets cancelled. So you get sine of initial theta is minus 1. Quickly tell me, sine of what angle is minus 1?
270, sir.
270. Okay. That is 3 pi by 2. 3 times of 90 degrees, 3 pi by 2. You can also write it as minus pi by 2, minus 90 degrees. Plus 270 degrees is same as minus 90 degrees. So we are going to take theta initial as minus pi by 2. You can take 270 also, 3 pi by 2. Nothing wrong in that. You can add one more 360 degrees to that. Okay. So 270 plus another 360 degrees. 570 plus 60. 630 degrees also you can take. Nothing wrong in that. Okay. So you must be knowing that trigonometric equations have infinite solutions. Which solution you choose is your choice. Or depending on options, you will have to choose. Fine. So let's take theta initial as minus pi by 2. Okay. Theta final, will keep it as theta itself. So theta initial is minus pi by 2. Therefore, the left hand side of the integral, which was integral dx by root of a square minus x square from minus a to x, has now effectively changed to theta from minus pi by 2 to some random value. Okay. Then how do you write this? You write this as theta minus of, okay, upper limit minus lower limit, minus pi by 2. Or wait, just a moment. Let us simplify this a little bit. We got this as integral d theta, which became theta itself, and we still have to substitute limits theta initial to theta final. Okay. Now, To integrate this, we had used the substitution x is equal to a sine theta. So you can say sine theta is x by a, or you can say theta is sine inverse of x by a. Therefore, the integral of this left hand side, integral dx by under root a square minus x square, is effectively sine inverse of x by a. Now we'll substitute limits. X initial, which is minus a, to x final, which is some random x. Okay, let's keep the equation in terms of x itself because we are trying to derive a relation between x and t, position time equation. Now substitute upper limit. Sine inverse of x stays as x minus, substitute lower limit now. Sine inverse of minus a divided by a. Okay, upper limit was x. I substituted that here. Lower limit was minus a. I substituted that here. And what did we have on the right hand side? We had omega into t on the right hand side of the equation here. Fine. Now a divided by a is 1, minus a divided by a is minus 1. Sine inverse of minus 1, I'm going to take it as minus pi by 2. As Aishwarya said, it can be 270 degrees, 3 pi by 2 also. There are infinite solutions that you can think of. I'm going to take it as minus pi by 2. Therefore, sine inverse of x by a, send the minus pi by 2 that side. Okay, this minus minus cancel, it becomes a plus pi by 2. But when it goes to the other side, it becomes minus pi by 2 again, is equal to omega t minus pi by 2. Now send the sign to that side. You get x by a is equal to sine of omega t minus pi by 2. Now send a to that side. You finally get x is equal to a sine omega t minus pi by 2. You see that term omega appearing in this equation. We had replaced k by m with omega square actually. So omega is under root k by m. That term appears here. Okay, that is why we had replaced k by m as omega square, because here you would have gotten under root k by m, which would have made this equation very tedious to write. It's simpler to express it in terms of omega. That's why we replaced k by m with omega square. So we get omega here. Okay, so finally we have gotten somewhere. We got x as a function of t. But remember, this is not the general equation. This equation assumed that initially the particle was at negative extreme. For that case, we got this equation. Okay, let's go through the derivation once again very quickly. First, we had derived Vx relation. From where? From the condition for SHM. The condition for SHM is A is equal to minus k by m into x, or A is equal to minus omega square into x. Acceleration was replaced with V dv by dx. So V dv by dx is equal to minus omega square x. Integrate both sides, substitute limits. We got a Vx relation. Fine. And this Vx relation doesn't depend on the limits actually. It doesn't matter. I mean, depending on the position, you can tell what is the speed. Okay. So we got Vx relation. Once you know Vx, we equated that to dx by dt, because velocity is rate of change of displacement with respect to time. Keep the x terms on one side, t terms on one side, and integrate both sides. We arrived at this final equation. Okay, this equation assumes initial position is minus a. In the Vx relation, I told you limit doesn't matter because we knew for sure that at extreme position velocity is 0. So we used a limit which we were sure of. Okay, so it doesn't finally appear in that equation. Here, at t equal to 0, we assumed the position is minus a. So the equation changes according to that. Because as the object oscillates back and forth, at extreme positions, the velocity must be 0 anyway. You have no option. You have no choice there. But as the object oscillates back and forth, which instant you call t is equal to 0 is your choice. Velocity 0 is not your choice, but time 0 is your choice. That is why I'm saying this equation that we got, the position time equation that we got, depends on where the object initially is. Okay, where you assume it is at t equal to 0, the equation changes based on that. We assumed it is initially at minus a, so we got an equation like this. Generally, the equation would be like this. X is equal to a sine omega t plus some constant. See, where did we get this minus pi by 2 from? If you remember, the minus pi by 2 came from the fact that it was at x is equal to minus a. We got sine inverse of minus a divided by a, that is sine inverse of minus 1. Sine inverse of minus 1 is minus 90 degrees. That is where we got that minus pi by 2 from. Okay, these two are linked to each other. So depending on where the object initially is, you will get this constant. This constant is called phase constant. And this entire bracket is called the phase of oscillation. You'll understand all these terms when we solve some problems, or when we actually visualize motion based on this equation, you'll understand. Okay, that bracket omega t plus phi, whatever is there inside the sign bracket, is called phase of oscillation. And you know a is called amplitude of oscillation. And what is x? In all this derivation, x is displacement from mean position. Don't confuse x for actual position. X is the displacement from mean position of the oscillating object. So this is the general position time equation of an object executing simple harmonic motion. All this came from a is equal to minus omega square x. Or you can say all this came from f is equal to minus kx. Force proportional to displacement from mean position, exactly opposite direction. That is the condition for SHM, and under that condition only this equation is valid. And it's not compulsory that you take it as sine, you can take it as cos also. Why? You look at this. We did integration by substitution here, where we substituted x as a sine theta. You could have substituted x as a cos theta as well. Then it will become under root a square into 1 minus cos square. Here we got, like in this case, we got a cos theta, and that cos theta got cancelled. That's fine. If you substitute x as a cos theta, you will get a sine theta here. Okay. And the final equation will be a cos something. Sine can be converted to cos, not a big deal. Okay, so the general equation, general position time equation of an object executing simple harmonic motion can be written like this. You can also write it as x is equal to a cos omega t plus phi. You can convert one from, one to the other also. We'll do all that while solving problems. Okay, we'll stop it here for today. Let us quickly recollect what all we discussed.